Welcome, everyone. In this session, we explore one of the most vital but often underappreciated domains in electronics, pulsed circuits. These circuits are the beating heart of high-speed communication systems, radar transmitters, oscilloscopes, switching regulators, and nearly every digital system. Today's goal is not just to understand how pulsed circuits work, but to go deep into the physics of pulses, how they interact with real-world components, and how to model, analyze, and measure them effectively. Let's begin by clearly defining what a pulse is. A pulse is a time-limited electrical signal that quickly transitions between two distinct states, typically a low state and a high state. The most common form is a square or rectangular wave pulse, but pulses can also be triangular, trapezoidal, or even exponentially shaped depending on the circuit's response. Now let's break down the standard parameters that define any pulse. The amplitude is the maximum value the pulse reaches in its high state, typically measured in volts or amps. Amplitude determines energy per pulse. The rise time is the time it takes for the signal to rise from 10% to 90% of its final amplitude. Why 10% and 90%? Because the extreme edges can be affected by noise and parasitics, so engineers standardize to the clean middle section. Rise time is limited by how fast charges can redistribute in the circuit. Parasitic capacitance slows voltage changes. Parasitic inductance resists sudden current changes. A perfect square edge does not exist in real circuits. Rise time always depends on bandwidth and parasitic elements. The fall time is the reverse. It is the time for the signal to drop from 90% to 10% of its amplitude. The pulse width is how long the signal stays in its high state. This directly controls energy delivery and data encoding rate. Repetition interval is the time between the start of one pulse and the start of the next. The reciprocal gives the pulse repetition frequency. The duty cycle tells us how much of the total time the pulse is high. So far, these are definitions, but let's look at the physical origin of a pulse. When you switch a circuit on, electrons don't teleport. They accelerate under an electric field, filling parasitic capacitances. That's why rise times aren't instantaneous. In circuits with inductance, current doesn't immediately reach its maximum. Inductors oppose sudden current changes, delaying current rise. Each transition is an exchange of energy. Capacitors store and release energy in electric fields. Inductors store and release energy in magnetic fields. A perfect vertical edge would require infinite frequency components. Real systems have finite bandwidth, which smooths sharp edges. Up to now, we've talked about pulses in their ideal mathematical form: perfect square edges, instantaneous transitions, no distortion. But in the real world, pulses are never ideal. When you apply a voltage pulse to a circuit, you're not just flipping a switch in empty space. You're interacting with real physical materials that obey the laws of electromagnetism. Let's break down exactly what happens. When a pulse is applied to a conductor, electrons must rearrange themselves to establish the new voltage level. Conductors, wires, and PCB traces are not just perfect wires. They behave like distributed capacitors. Every trace has parasitic capacitance to ground or to neighboring traces. When you suddenly raise the voltage, those parasitic capacitors must charge to the new potential. The rate of this charge redistribution determines how fast the voltage can rise, which the TR is about source resistance times parasitic capacitance. Now, whenever current changes, it creates a changing magnetic field around the conductor. According to Lenz's law, this changing magnetic field induces a voltage that opposes the change that created it. In other words, rapidly increasing current means induced voltage tries to slow it down. Rapidly decreasing current means induced voltage tries to keep it flowing. This behavior is modeled as inductance in wires, loops, and PCB traces. Mathematically, V is equal to L times d1 over dt. A fast pulse has a very high di over dt, so even small inductances generate significant opposing voltages, causing delays, rounded edges, or ringing. This is why ground loops, long wires, or coils make clean pulse transmission difficult. When a pulse travels along a transmission line, like a coaxial cable or PCB trace, it behaves as an electromagnetic wave. If the impedance of the line doesn't match the impedance of the source or load, some of the energy is reflected back toward the source. These reflections interfere with the original pulse, causing overshoot, ringing, and double edges or echoes. Now, let's analyze how a simple RC circuit responds when you apply a pulse. This is fundamental because almost every real circuit has some RC behavior due to resistive and capacitive elements, even if unintended. When a DC voltage is suddenly applied across an RC series circuit, the capacitor voltage grows as VC equal to V0 times 1 minus e to the power of minus t over RC. Here, R is resistance, C is capacitance, RC is the time constant. The time constant tells us how quickly the capacitor charges. At t equal to 0, the capacitor initially behaves like a short circuit, so current rushes in freely. At t equal to RC, the capacitor voltage reaches its 63% of full charge voltage. 63% charge. At t equal to 5 RC, the capacitor is essentially fully charged. Physically, this is due to charge accumulation on the plates, creating an electric field that gradually resists further current flow. Now, what happens if we apply a short pulse, one that turns on only briefly before turning off? The pulse is too short for the capacitor to charge significantly. The voltage only rises a little before the pulse ends. When the pulse ends, the capacitor discharges immediately, producing a brief spike in the output. Because the capacitor only responds to the edges of the pulse, the circuit acts like a differentiator, so we have positive spike on the rising edge and negative spike on the falling edge. This is used in edge detection circuits, such as timing or triggering systems. Think of trying to fill a bucket with water, but turning off the faucet after just a fraction of a second. The water level barely rises before draining back. Now consider a long pulse. The capacitor has enough time to charge almost completely. When the pulse ends, the capacitor discharges exponentially, so the output follows the input, except for the gradual charge and discharge slopes. Over multiple long pulses, the RC circuit can act as a simple integrator, averaging the signal over time. This is used in smoothing circuits for PWM signals and low-pass filters in audio or sensor systems. Now let's analyze how an RL circuit, a resistor and inductor in series that responds to a pulse. Unlike an RC circuit, where capacitors control voltage buildup, in RL circuits, the inductor governs current buildup. The key point is that inductors resist changes in current, while capacitors resist changes in voltage. When a step voltage is suddenly applied to an RL circuit, the current follows as I equal to pulse voltage over R times 1 minus e to the power of Art over L. At the moment the step is applied, current is 0. Why? Because the inductor initially acts like an open circuit. This is due to Lenz's law. A sudden current change creates a changing magnetic field, which induces a voltage opposing that change. The faster you try to push current, the stronger the opposing EMF. Physically, it takes time for the magnetic field around the inductor to build up. After about 5 time constants, the magnetic field is fully established, and the inductor behaves like a short circuit for DC. Current reaches a steady value determined by Ohm's law. Now let's apply a pulse instead of a step. The pulse turns off before the current has had time to rise significantly. The magnetic field never fully develops. The current remains very small, then decays rapidly when the pulse ends. This is useful when you want to block short pulses. RL circuits act like a low-pass filter for current. In the long pulses, once the pulse ends, the current doesn't stop instantly. It decays exponentially as the stored energy in the magnetic field is released. Physically, the collapsing magnetic field induces a voltage that tries to keep the current flowing even if the source is removed. In many applications, we don't just want to send or receive pulses. We want to manipulate them. Why? Because by reshaping pulses, we can detect events, trigger timing circuits, or generate new waveforms. One of the simplest and most powerful ways to manipulate pulses is with RC analog filters configured as differentiators or integrators. Let's explore both in detail. An RC differentiator is typically a capacitor in series with the input and a resistor to ground at the output. The capacitor passes changing voltages but blocks steady-state DC after charging. When the input voltage jumps suddenly, the capacitor doesn't allow an immediate change in voltage across it. A large charging current flows briefly through R, creating a sharp voltage spike. Once the capacitor charges to the new voltage, current stops and output returns to 0. So the differentiator essentially reacts only to changes, ignoring steady levels. An RC integrator is simply the opposite configuration. a resistor in series with the input and a capacitor to ground at the output. Here, the capacitor accumulates charge over time, effectively averaging the input signal. When a square wave is applied, the capacitor voltage can't change instantly. It takes time to charge or discharge. Instead of following the input abruptly, it smooths the transitions, turning sharp edges into gradual slopes. If RC is much larger than the pulse width, the output barely moves. Let's bring our discussion of pulses into a real-world high-power application. Radar is a perfect example of why understanding pulse behavior timing, power, and signal integrity is critical. A radar system works by transmitting short, high-energy pulses of radio frequency energy, waiting for reflections from objects such as aircraft or ships, measuring the time delay to calculate distance. The shorter and more precise the pulse, the better the radar can resolve objects and distinguish between closely spaced targets. Impedance mismatches in transmission lines or antennas cause energy to bounce back. The radar transmitter, transmission line, and antenna must all have matched characteristic impedance. Proper matching ensures maximum energy transfer and prevents ringing or standing waves. Measuring pulses accurately is not as simple as just connecting an oscilloscope. Pulses are fast, high-frequency events with sharp transitions. Capturing their true shape requires specialized instruments and proper setup. Let's break this down. Why bandwidth matters. A pulse is not a single frequency signal. It's made up of many high-frequency components. The sharper the rise time, the higher the required bandwidth to display it without distortion. To faithfully reproduce the shape, we often need 10 times the highest frequency component. If the bandwidth is too low, edges look slower than they really are. Overshoot and ringing might not appear, and rise time measurements will be inaccurate. When measuring low frequency or moderate speed pulses, use high impedance probes. Why? To avoid loading the circuit. A low impedance probe draws current and changes the pulse's shape, especially in sensitive circuits. At high speeds or transmission line environments, you must use matched impedance probes typically. Why? If probe impedance does not match the line impedance, then reflections occur, which means distorted pulses. Properly matched probes absorb energy cleanly. The oscilloscope samples the signal at discrete time intervals to accurately reconstruct a pulse. For nanosecond or sub-nanosecond pulses, you need gigahertz range sampling rates. Once the setup is correct, we can measure key pulse parameters like peak voltage, rise and fall times, overshoot, and ringing amplitude and frequency. Let's review some engineering tip. Always keep probe ground leads short because long leads act like antennas and add inductance. Use 50 ohm termination at high frequencies to prevent reflections. Compensate probes before measurement to ensure flat response. Use average or single shot mode for repetitive or single pulse capture. Digital logic fundamentally relies on pulses as the backbone of its operation. Every element in a digital system, flip-flops, counters, shift registers, and clock distribution networks that operates based on the precise timing and sequencing of voltage transitions. A flip-flop, for instance, stores a logic state only when triggered by a clean, well-defined clock pulse, while counters and shift registers rely on sequential pulses to advance their states in perfect synchrony. The clock signal, often referred to as the heartbeat of a digital system, is nothing more than a continuous train of carefully shaped pulses that dictate when data is latched, processed, or moved through different logic stages. However, when these pulses are not shaped or timed correctly, digital systems can fail in subtle yet catastrophic ways. Poor pulse shaping can lead to metastability, a condition where a flip-flop fails to resolve into a stable logic state due to ambiguous or noisy timing at its input. This metastability can propagate through a system, causing random and unpredictable logic errors. Similarly, if pulses are too narrow, too wide, or distorted by ringing or overshoot, they can produce glitches, which are false triggering events that make counters skip counts or shift registers misalign data. Even a single malformed pulse in a high-speed processor or communication interface can lead to corrupted data, system crashes, or complete functional failure. For these reasons, clean pulse generation is not just a design preference, it is an absolute requirement for digital system reliability. Engineers go to great lengths to ensure that clock pulses and control signals have sharp edges, consistent amplitude, and minimal noise. Careful attention is given to transmission line effects, impedance matching, and power supply decoupling to prevent reflections or timing jitter. In high-speed systems, specialized clock drivers and buffers are used to maintain pulse integrity across long traces or multiple logic stages. Simply put, the reliability and predictability of every digital device from microcontrollers to supercomputers depend on the integrity of its pulses.